We like to think the laws of physics are permanent, solid, unchanging, as if the universe signed a contract at the beginning of time and promised never to break it. That belief is comforting, and it might be completely wrong, because when you actually look at how physics works, not the slogans, the equations, you discover something awkward. The laws we trust are not written into stone. They are inferred from observation, and observations are local, temporary, limited. Here's the disturbing part. Nowhere in physics does it say the laws must remain the same forever. We assume they do because they've been stable for as long as we've been watching. But the universe is very old, and we've been paying attention for a very short time. That's like checking a clock for 1 second and declaring it will tick the same way forever. In fact, some of our best theories quietly allow the laws to drift, evolve, or even break under extreme conditions. Different eras, different energies, different rules. And if the laws can change even slightly, then everything we think is fundamental becomes provisional, which means physics may not be discovering eternal truths. It may be catching the universe in the middle of a phase, and that should make you nervous. What if the laws of physics are only temporary? Let's begin with a belief so common that most people never question it. The laws of physics are permanent. They were true yesterday, they are true today, and they will be true tomorrow. That assumption sits quietly underneath everything we do in science. We measure, calculate, predict, all on the faith that the rules won't suddenly change while we're not looking. But here's the uncomfortable fact. Physics does not guarantee that assumption. We treat the laws as eternal because they've behaved that way so far. But so far is not a principle of nature. It's a limitation of observation. And physics is very careful about confusing habit with truth. Laws are not commandments. One of the biggest misunderstandings about physics is the word law itself. A law of physics is not a command issued to the universe. It's a description. We observe patterns. We write equations that summarize those patterns. We test them again and again. When they keep working, we call them laws. But notice what's missing. No law comes with a warranty. Observation is always local. Every experiment you've ever heard of happened somewhere, at a certain time, at a certain energy, under certain conditions. Even our most precise measurements of gravity, electromagnetism, quantum behavior are samples taken from a tiny region of the universe's history. We are like someone who has read one page of a very long book and decided the grammar will never change. That confidence may be justified, but it is not proven. Why physicists rarely say this out loud? Physicists don't like to talk about changing laws, not because the idea is ridiculous, but because it's dangerous. If the laws can change, then prediction becomes conditional, and prediction is the backbone of physics. So instead, we quietly assume stability not as a belief, but as a working rule. That distinction matters. The universe has changed before. Here's something we often forget. The universe we live in now is not the universe that existed shortly after the Big Bang. Early on, temperatures were so high that atoms couldn't exist. Particles behaved differently. Forces we now think of as distinct were once unified. The rules didn't break, but they didn't look the same either. That alone should make you pause. Because if the laws once behaved differently, then permanence is already gone. Constants are only constant until they aren't. Take the so-called fundamental constants. The speed of light, the strength of gravity, the charge of the electron. We call them constants because as far as we can tell, they don't change. But again, as far as we can tell, is doing a lot of work. Physics does not explain why these numbers have the values they do. It merely observes that they seem stable within our window of measurement. And a window is not eternity, a subtle doubt hidden in the equations. Some of our most successful theories quietly allow for variation, not dramatic changes, not chaos, but slow drift, tiny evolution, changes so small they would be invisible to everyday experiments, but catastrophic over cosmic timescales. And here's the disturbing part. Nothing in the mathematics forbids this. Symmetry is not guaranteed forever. Modern physics loves symmetry. Symmetry simplifies equations. Symmetry explains conservation laws. Symmetry gives us elegance. But symmetry can break. We already know this. When conditions change, symmetries can collapse, revealing new behavior underneath. This happens all the time in condensed matter systems. It happened in the early universe. Why assume it can never happen again? Laws as emergent behavior. There is another idea that makes people uneasy. What if the laws of physics are not fundamental at all? What if they are emergent, meaning they arise from deeper rules, rules we haven't seen yet? The way temperature arises from molecular motion. Temperature feels fundamental. It isn't. It's a collective effect. If the laws of physics are like that, then they are not eternal. They are stable phases. A chilling analogy. Think about water. At low temperatures, it behaves like ice. At higher temperatures, it flows. At even higher temperatures, it becomes vapor. The underlying molecules don't change. The rules governing behavior do. Now imagine the universe is in one such phase right now. Comfortably stable, predictable, but not permanent. Why this idea is hard to swallow. People hear this and panic. They imagine gravity turning off tomorrow, or electrons refusing to behave. That's not the point. Physics is not suggesting sudden betrayal. It's suggesting humility. We don't know whether the rules we see are the final rules, and not knowing is not the same as being wrong. Stability is an observation, not a promise. So far, the laws have been remarkably stable. That's true, but stability does not imply eternity. Mountains are stable, stars are stable, atoms are stable. None of them are permanent. Why Feynman was skeptical of absolutes. Good physicists are suspicious of absolute claims. Whenever someone says always or never, it's worth checking what assumptions slipped in unnoticed. The history of physics is full of laws that seemed final until they weren't. Newton's laws didn't disappear. They were replaced by something deeper. They still work, but only within limits. That pattern should worry you. Replacement is not rebellion. When new laws appear, the old ones don't explode. They become approximations. Useful ones, local honest. Temporary ones, which means calling something a law is not the end of inquiry. It's the beginning, the most dangerous assumption of all. Here is the assumption hiding at the core of modern science, that the universe itself is stable enough for explanation. Physics works because the universe behaves regularly, but physics does not explain why it behaves regularly. It simply takes advantage of it. Why this is not philosophy sneaking in. At this point, people say, this sounds philosophical. It isn't. This is physics doing something it rarely does, questioning its own foundation. And physics has learned the hard way that foundations crack when you stop examining them. A thought that refuses to go away. So consider this possibility quietly, carefully. The laws of physics may be like the climate, stable for long periods, predictable within ranges, but capable of change under extreme conditions, not breaking, evolving. The first shock, if that's true, then everything we call fundamental is provisional, not false, not fragile, just conditional. And that realization changes how you look at physics, because physics stops being a search for eternal commandments and becomes a study of the universe's current habits, how changing laws could hide in plain sight. If the laws of physics were changing, you might expect fireworks, planets flying apart, atoms falling apart, time misbehaving. But that expectation is based on a very human mistake. We imagine change as dramatic. Physics prefers subtlety. Why big changes don't announce themselves? The universe is very good at hiding small effects. Tiny deviations get buried under noise. Slow drifts get mistaken for constants. Gradual evolution gets written off as error bars. And the more stable a system appears, the easier it is to miss its instability. That's the dangerous part. If the laws of physics change, they don't need to change much to matter. The tyranny of precision. Modern physics is extraordinarily precise. We measure quantities to many decimal places. We track variations with astonishing accuracy. That sounds reassuring. But precision can become a trap, because we compare today's measurements to yesterday's, not to eternity. If a constant drifts slowly over billions of years, no human experiment will notice. It would look perfectly stable within our lifetime. The speed of light problem. Take the speed of light. We treat it as a universal constant, and experimentally it behaves like one. But all we really know is this: it has not changed measurably within the slice of cosmic history we can observe. That is not the same as saying it has never changed, or will never change. Ratios versus absolutes. Here's a subtle but crucial point. We don't actually measure constants in isolation. We measure ratios. The speed of light relative to atomic transitions. The strength of gravity relative to particle masses. If everything changes together, we may never notice. That's deeply unsettling, because it means the universe could evolve its rules quietly, without leaving fingerprints we know how to recognize. When variation looks like calibration error, imagine measuring a ruler that slowly stretches. Every object you measure stretches with it. Your measurements stay the same. You conclude nothing changed, but the ruler did. Physics faces the same problem. Our measuring devices are made of the same universe whose laws we are testing. That creates a blind spot. The universe is not required to be convenient. We often act as if the universe is obligated to reveal its deepest secrets. It isn't. If changing laws are subtle enough, they could evade detection indefinitely. Not because physicists are careless, but because physics itself is self-referential, evidence we can't ignore. Despite this, physicists have looked carefully, and sometimes they've found hints, tiny anomalies, unexplained discrepancies, measurements that don't quite line up across vast distances or times. Most of these get explained away correctly as experimental error, but not all of them disappear easily, and that's where discomfort begins. The early universe was not playing by today's rules. One fact is beyond dispute. The early universe behaved differently. At extreme temperatures and energies, the forces we now consider distinct were unified. Electromagnetism and the weak force merged. Gravity may have behaved differently. Particles didn't have the masses they have now. The laws didn't merely look different. They were different. Different conditions is not the same as same laws. People often say, the laws didn't change, the conditions did. That may be true, but it hides an assumption that the laws themselves are immune to conditions. Physics does not guarantee that. It merely observes that under known conditions, certain behaviors repeat. Phase transitions are law changes in disguise. Consider phase transitions: water freezing, magnets losing magnetization, superconductivity appearing. At a phase transition, the effective laws governing behavior change. Same underlying particles, different rules. Why assume the universe itself cannot undergo such transitions? Laws as low-energy approximations. Many physicists now suspect that the laws we know are not fundamental. They are low-energy approximations, effective theories. They work because we live in a calm, cool, late universe, not because they are eternal. The illusion of finality. Every generation of physicists believes they are close to the final laws. Every generation has been wrong. Newton thought mechanics was complete. Maxwell thought electromagnetism was final. Early quantum physicists thought the framework was settled. Each time, deeper layers appeared. Why should this time be different? Why Feynman distrusted final theories? Good physicists don't distrust equations. They distrust certainty. Whenever someone says, this is the final answer, history advises skepticism. Nature has a habit of revealing new behavior just beyond the boundary of confidence. The slowest changes are the most dangerous. A law that changes quickly would be obvious. A law that changes slowly would be invisible. And invisibility is not evidence of absence. It is evidence of patience. Cosmology's uneasy role. Cosmology tries to infer laws from the largest possible system, the universe itself. But it only has one universe to work with. No control group. No repetition. That makes it uniquely vulnerable to mistaken assumptions. Constants may be environmental. Here's another unsettling idea. What we call constants may be environmental, like temperature or pressure. They appear fixed locally, but vary across larger scales. If that's true, then physics is studying a local climate, not a universal law book. Why this hasn't broken physics yet? If laws were changing, why hasn't physics failed catastrophically? Because effective laws are robust, they tolerate small deviations. They continue to work until pushed too far, just like Newton's laws. They didn't suddenly stop working. They quietly became incomplete. The second shock, let's pause and take stock. So far we've learned, laws are inferred, not guaranteed. Measurements are local and relative. Subtle changes could go unnoticed. Early universe laws differed. Known laws may be emergent ported. This doesn't mean the laws are changing. It means physics cannot rule it out. And that is the important part. Why this makes physics more honest, not weaker. Some people think this undermines science. It doesn't. It strengthens it. Physics works not because it claims certainty, but because it questions it. Doubt is not failure. It is discipline, a quiet, unsettling possibility. So consider this. Without panic or drama, the universe may not run on eternal rules. It may run on stable habits, habits that last a very long time, long enough to build galaxies, long enough to build life, long enough to build physicists. But habits can change. What enforces the laws right now, and why that question is dangerous? At this point, a reasonable person might say, fine, maybe the laws of physics could change, maybe they emerged, maybe they're not eternal, but clearly something is enforcing them right now. That sounds sensible, and it may be completely wrong, because enforcement is a human idea. Physics does not recognize enforcers. The hidden assumption we never examine. When we talk about laws, we imagine something like a rule book. Rules are written. Rules are followed. Rules are enforced. But the universe does not consult a manual. An electron does not check Maxwell's equations before moving. A particle does not obey quantum mechanics. A planet does not respect gravity. Those words are metaphors. And metaphors become dangerous when we forget they are metaphors. Laws don't push, they describe. This is one of the most important ideas in physics, and it's often misunderstood. Laws do not cause things to happen. They describe what happens. Gravity doesn't make a rock fall. The rock falls. And gravity is the name we give to the pattern. That distinction seems small. It isn't. Because if laws don't cause behavior, then they don't need enforcement. They are summaries, not instructions. Patterns without a policeman. Imagine watching a crowd from above. People form lanes. They avoid collisions. They cluster and disperse. No one enforces the pattern. The pattern emerges. Physics may be like that. The laws we write down may be the stable patterns that survive, not the rules that command. Stability does not require authority. A crystal does not need a supervisor to maintain its structure. It holds together because the configuration is stable. Atoms arrange themselves in certain ways because other arrangements fall apart. Stability selects behavior, not authority. The laws as survivors, not rulers. This leads to a deeply unsettling idea. The laws of physics may not be imposed on the universe. They may be the behaviors that didn't self-destruct. Configurations that were inconsistent collapsed. Unstable patterns disappeared. Only the durable ones remained. What we call laws may be the survivors. Why this sounds backward, but isn't. We're used to thinking, first the laws, then the universe. But physics may be telling a different story. First behavior, then description. We notice regularities because they persist. Irregularities vanish, and persistence looks like lawfulness. The trap of asking why these laws, this is where many discussions go wrong. People ask why these laws exist instead of others, but that question assumes all laws were equally possible. Physics does not say that. Some structures may never have been viable. Some possible laws may not even define coherent realities. Consistency as the only judge. Consider mathematics. Many formal systems can be written down. Most of them collapse under contradiction. Only consistent systems survive long enough to be interesting. No one enforces consistency. Inconsistency simply fails. The universe may operate under the same logic. Why nothing needs to hold the laws in place? If the laws are stable patterns, then nothing needs to hold them. They hold themselves, not by force. By coherence, when conditions drift too far, patterns change. New effective laws appear. Old ones fade. No rebellion required. A universe without guarantees. This is where the discomfort deepens. If nothing enforces the laws, then nothing guarantees them. They persist because conditions allow them to persist. That's it. No promise of eternity. No assurance of permanence. Just ongoing stability. Why this doesn't mean chaos. At this point, people imagine disorder. They imagine randomness erupting everywhere. That fear misunderstands stability. Stable systems resist change. Deeply stable systems resist it strongly. The laws we observe may be extraordinarily stable, just not invincible. The analogy of a riverbed. Think of a river. Water flows along predictable paths. It follows channels. The channels feel permanent, but they're not. Over long time scales, they shift. Not suddenly, not dramatically, quietly. The water keeps flowing. The rules of flow change. Physics as the study of channels. Physics may not be discovering eternal truths. It may be mapping the channels reality currently flows through. That mapping is incredibly useful, but it is not a declaration of permanence. Why Feynman was wary of absolutes. Good physicists avoid saying must without qualifiers. Nature has embarrassed certainty too many times. Whenever a law is declared final, history gets ready to correct it, not by destroying it. By contextualizing it, the universe doesn't owe us predictability. This is another illusion, worth discarding. We act as if predictability is a feature of reality. It isn't. It's a condition that happens to hold locally, temporarily. Physics works because predictability holds enough, not because it must. Order without obligation. The universe doesn't promise order. It exhibits it. And exhibiting something is not the same as guaranteeing it forever. The third shock. Let's pause and gather the consequences. If laws are descriptions, not commands, emergent, not imposed, stable patterns, not enforced rules, then the universe is not governed. It is self-organizing, and self-organizing systems can change their organization. Why this makes physics humbling. Physics doesn't sit above the universe, issuing decrees. It watches, it measures, it summarizes, and it revises. That humility is not weakness. It's the reason physics works at all. The edge we're standing on. We are now at a strange boundary. On one side, predictability, stability, reliable laws. On the other, contingency, emergence, possible change. Physics lives on that edge. Not comfortable, not dramatic, honest. The question we can't avoid anymore. If nothing enforces the laws, and if they persist only because conditions support them, then one final question becomes unavoidable. Why are the conditions right now? Why does the universe currently sit in a stable phase? Why not another? Where this leads next? That question takes us beyond mechanics, beyond equations, beyond even cosmology, because now we're asking not about laws, but about phases of reality. And that's where the idea of temporary laws stops being speculative and starts becoming unavoidable. If the laws are temporary, what does that say about reality and about us? By now, something important should have shifted in the way you think. Not collapsed, not exploded, just loosened. Because once you seriously consider that the laws of physics might be temporary, the universe stops looking like a perfectly engineered machine and starts looking more like a stable phase, a long-lasting one, but not a guaranteed one. And that changes the meaning of explanation itself. The final illusion that reality owes us stability. We grow up with an unspoken belief that reality is supposed to make sense, that the rules are supposed to hold, that predictability is somehow owed to us. Physics never promised that. Physics only reports what has worked so far. The idea that the laws must remain fixed forever is not a scientific conclusion. It's a psychological comfort. Stability is a condition, not a right. Everything we know that appears permanent turns out on inspection to be conditional. Atoms are stable until they aren't. Stars are stable until they burn out. Galaxies are stable until gravity reshapes them. Why should laws be any different? Why should they be exempt from the very impermanence they describe everywhere else? The universe as a phase, not a final state. Think again about phases. Ice feels solid. Liquid water feels inevitable. Steam feels like a breakdown. But none of them are fundamental. They are arrangements that persist only while conditions allow them. The universe may be no different. The laws we observe may correspond to a low-energy, late-time phase of reality, calm, structured, predictable, not because it must be so, but because this phase is stable right now. Why this doesn't mean doom tomorrow. This is important. Temporary does not mean fragile. A mountain is temporary. So is the Sunday. Temporary things can last billions of years. So the idea that the laws might change does not imply catastrophe. It implies humility, physics without a safety net. If the laws are not eternal, then physics is not the discovery of ultimate truths. It is the mapping of reliable behavior within a window, a remarkably successful window, but still a window. That does not weaken physics. It defines it accurately, the deepest shift from must to happens. The most profound change here is subtle. Physics stops saying, this must be the way reality works, and starts saying, this is how reality behaves under these conditions. That shift removes inevitability but not usefulness. Why this idea feels unsettling? Because it removes guarantees. If laws are temporary, then reality is not anchored by necessity. It is anchored by coherence. And coherence can fail not suddenly, not violently, but by drifting into something else. The universe without an owner's manual. There is no instruction booklet attached to reality. No clause that says, these laws shall remain in force for all time. There is only behavior that repeats until it doesn't. And repetition is not obligation, meaning in a provisional universe. At this point, people usually ask the wrong question. They ask, does this make life meaningless? It doesn't. It makes meaning local, temporary, earned. Meaning does not require eternity. A conversation does not need to last forever to matter. A life does not need cosmic permanence to be significant. You are not protected by the laws. You are enabled by them. Here's a quieter truth. The laws of physics do not exist for you, but they make you possible. They form a stable environment where complexity can arise, where memory can persist, where thought can occur. That stability does not need to be eternal to be extraordinary. The strange role of observers. Observers like us exist only in regions where laws are stable enough. That's not coincidence, that's selection. If the laws were wildly unstable, there would be nothing to observe them. So the fact that you are here tells you something important. You live in a calm phase of reality, not a guaranteed one, a fortunate one. The final question physics refuses to answer. There is one question physics cannot answer and never promised to. Why is there this phase rather than another? Why now? Why this stability? Physics can describe the phase. It can model it. It can predict behavior within it. But it cannot justify it. And that is not a failure. It is a boundary. The universe doesn't need to explain itself. This may be the hardest idea of all. The universe does not owe us an explanation for why it exists in this form. Explanation is something we seek. Reality does not participate in that need. It simply behaves. The quiet conclusion. So let's return to the original question. What if the laws of physics are only temporary? The most honest answer is this: then physics is not a book of eternal rules. It is a record of long-lasting habits, reliable habits, deep habits, habits stable enough to build galaxies and minds, but habits nonetheless. Why this is not pessimistic? This perspective does not cheapen science. It dignifies it. Physics becomes what it truly is, a disciplined way of listening to the universe without assuming it will speak the same way forever. If you really love physics, you don't demand certainty from it. You respect its honesty. And honesty sometimes means admitting this. The laws work. They work beautifully. They may work for a very long time, but physics does not and should not promise they will never change. Nothing explodes at the end of this story. The equations still work tomorrow. The atoms still bind. The stars still shine. But something subtle has changed. You no longer confuse reliability with eternity. And that is a more accurate way to see reality.